The last type of bonding we have is ionic bonding. Ionic bonding is a bond between a metal and a nonmetal. So you have an item from the left side of the periodic table and an item from the right side of periodic table. During this bonding, we transfer electrons. One atom gives them up, the other atom or atoms accept them. This is created by electrical force of attraction, or an EM force, is the attractive force between positive and negative ions. You can kind of think of it like magnets. An example would be sodium chloride. We seem to use table salt for a lot of examples. It's just something common that we all understand. So sodium chloride, table salt, is formed due to ionic bonding. The metals will lose electrons and become positively charged. The nonmetals will gain electrons and become negatively charged. So the left element will be positive, it's a metal. The right element will be negative, the nonmetal. When they come together, they form a neutral ionic bond, meaning their charge has to equal 0 when these two items form together or make their bond. Some common properties for ionic substances. They are crystalline, so the ions are arranged in geometric shapes. They have high melting points. Pretty much every ionic compound that I know of is a solid at room temperature and very hard to melt. They can conduct electricity in a liquid or solution form, so meaning if it's molten or if it's dissolved in water, it can conduct electricity, and most of them are soluble in water. So an example would be sodium chloride, and we have the picture here. Sodium is on the left, chlorine is on the right. We're going to do Lewis dot structures when we draw them instead of Bohr models. Sodium has one valence electron, one dot in its outermost shell, and chlorine has 7 valence electrons, 7 dots in its outermost shell. So keep in mind, sodium's to the left, chlorine is to the right. So sodium will give up one electron and it will go to the chlorine. All right, so that took a little longer than I thought. So sodium gave up the one electron and now chlorine has 8 electrons and sodium is missing one. So it has a positive 1 charge because it has less electrons than protons. Chlorine has a negative 1 charge. It has more electrons than protons. So if we're doing Lewis dot structures, we could draw 1 dot for the sodium and 7 dots for the chlorine, and that sodium's green dot will go to the chlorine, giving sodium a +1 and chlorine a -1 charge. And that would be the proper way of drawing it. Magnesium chloride is another example. This guy, magnesium, has 2 dots to give up. However, chlorine can only receive 1 extra dot. So we need a second chlorine atom to take on magnesium's extra dot, extra electron. So we have 1 magnesium, but we need 2 chlorines to make it neutral. Magnesium makes a +2 charge. Each chlorine is -1. So a +2 plus 2 times -1 gives us that 0 charge. When we're writing, we need to use superscripts or exponents. We will use positive superscripts if an atom has lost an electron. We will use negative superscripts if an atom has gained an electron. I cannot emphasize enough that our nonmetals are negative. They have extra electrons. Electrons are negative. When writing an ionic formula for magnesium chloride will be an example, We write the formula for the metal first, and then we write the charge. So magnesium's symbol is Mg. His charge is +2. That's because it's in the second column of the periodic table, and we were to learn last unit that yields a +2 charge. Then we write the symbol for the nonmetal and its charge. Chlorine symbol is Cl with a -1 charge because it is in the halogen family. The formula for the compound must have the net ionic charge of 0 or be neutral. The easiest way to do this is crisscross, and I will show you examples how to do that in our handout after this is concluded. So we have magnesium with a +2, Cl with a -1. We draw an arrow and take our 2 down. Don't literally have to draw an arrow, but we often do, and write the 2 as a subscript, meaning written down low, smaller, behind the symbol. The 1 would come down, and we don't really have to write the 1, but the number of the oxidation number of each element becomes a subscript of the other one. So as of right now, if we crisscross, we would have Mg1, Cl2. When the subscript equals 1, we don't usually write it. By writing the symbol, you have that element. If you have more than one of an element, it must have a subscript. So we're going to erase that 1. When writing ionic formulas, it tells us some information. It tells us the number and type of atoms of the elements in the compound. So magnesium chloride has 1 atom of magnesium and 2 atoms of chlorine. Ionic compounds with transition metals. Sorry, formatting seems to have taken out the transition metal part of that header. Because transition metals have special electron arrangements, they are able to form different types of ions. For example, copper can be a +2 or a +1 charge, so it has +1 or +2 ions. And you can see that by the superscripts written behind the copper symbol. We must show which ion is present using Roman numerals or the stock system. The Roman numeral is the same as the charge on the ion. A little review of Roman numerals. The Roman numeral 1 is +1, 2 is +2, 3 +3, and 4 +4. Let's look at an example of another transition metal. We have iron, subscript 2, O, subscript 3. Since when we write formulas, we use the crisscross method, we can do the opposite and we can do crisscross up. So the subscript for the O is a 3, so we'll cross that up, and that tells us iron's charge is +3. So the name becomes iron, Roman numeral 3, oxide. We also have polyatomic ions. Sometimes atoms bond but do not get all of the electrons they need. So hydrogen and oxygen, we're used to them being H2O. But hydrogen and oxygen can also just make hydroxide ion, OH, but it has an extra electron, a -1 charge. These compounds are stable, but will pick up an extra electron to fill out their outer shell, giving them the -1 charge. So that would be our hydroxide ion. These molecules will form another bond to become stable. So hydroxide will form with metal and will then become stable. Polyatomic ions are ions made up of more than one element. When you need multiples of a polyatomic ion, you need to use brackets or parentheses. A few examples of polyatomic ions are nitrate, sulfate, carbonate, and phosphate. So when we write these formulas, we have Mg +2, magnesium hasn't changed from before, but now we're going to use nitrate for our anions. We'll bring the -1 down, but keep in mind we don't actually write that, so we'll just pretend we did that. And then we bring our +2 down. But notice that looks like N with 32 oxygens, so we can't leave that alone. So to make NO3 have a subscript of 2, you must put brackets around all of the NO3, or parentheses, whether you like to do brackets or parentheses. So now it doesn't look like 32 oxygens, it looks like 2 NO3s. The formula of the polyatomic ion will never change when writing formulas. So there'll be a tutorial on how to do the crisscross method using this practice grid, and then you also have another practice grid for you to give it a try on your own.